Hey guys, welcome to another session. And today we're talking about hash collision probability. This is especially useful for hardware designers who want to model their hash tables inside hardware, and they want, because of limited resources, they cannot have infinitely sized linked lists to deal with collisions. So let's try to understand a little bit as to what this problem really is and how, as hardware developers, we deal with this. So what is a hash table? A hash table usually is a data structure that has a key and value kind of pairs that are stored there. How it's stored, most people never really think about it, but the way it's done is that when you provide a key, it could be a bunch of bytes, text, anything like that. And then there is a hash function that will crunch all this data and produce some address. And that address is basically just another number of bits. Let's say you feed in 200 bytes and then output comes as 3 bytes or 8 bytes or something like that, and this 8 bytes are indexed into this table as address, and then you store the value there. So that's the general concept of a hash table. Now what happens is that when you try to do this, it is possible, there is a small probability that multiples of these keys would go into the same index element, and therefore they all want to go here. Let's say they all want to go to 0, or they all want to go to 2 or something like that. When this happens, we call this as a collision. And the way collisions are handled is that you have usually not just one entry, but multiple entries, and you have things like either you have multiple columns and you can just compare all of them, or you have linked lists, some sort of a chaining, or you even have open addressing that you don't have to store here. You can store vertically down. So if this is the 0 is the value, you can go look in the next value, the next value, the next value. So you can go down this way. So there's many schemes. One very special scheme is called cuckoo hashing, where instead of having one table, you can have two tables and two hash functions, and that is fairly significant improvement in the probability of collisions. But we won't go into that. We won't go into collision handling. We just want to cover the surface, which is what is this collision and how normally would a hardware designer start to think about it, right? So a mathematical framework is what we want to touch upon. So next, let's look at the probability. So one of the famous problems is balls to bins problems, which is if you have m balls and n bins, and if you throw the balls randomly into one of the bins, what's the probability of a bin getting exactly k balls? And that is kind of the problem that we are dealing with here, that if we have m entries that are going into n hash rows, right, then if we want to make sure that each row can only handle up to k entries, then what is the probability that each row would be full? And for that, the way mathematically is handled is that you can choose k items from m items by using the m choose k function. Once you have the m choose k, now you can say what is the probability of a ball going into your specific bin. Let's say we pick a bin, so 1 by n is the probability, and then k balls have to go there, so 1 by n to the power k, and the remainder of the m minus k balls have to go in the remainder of the bin. So the probability is 1 minus 1 over n, which is one chosen bin that we used here. All the other bins would carry the remainder, so 1 minus 1 over n to the power m minus k. So that is the probability, and this is the function. Keep an eye on this function, because we will basically stick to this function as an indicator of how good our hash is. Again, this is the balls to bins problem, and this is our answer. And using this, we will try to see how our hash functions perform. So now let's try out an example. If we have 500 balls and 1,000 bins, and then each ball is independently thrown into the random bin with equal probability, what is the probability that a specific bin will have 4 balls? Let's say just this is the problem. So the naive approach might be, you might say, hey, the probability is 1 over 1,000 that ball might end up in my bin, and 4 of those balls have to hit my bin, so 1 over 1,000 times to the power 4, and that is 10 to the minus 12. That's a very small probability that you will end up with 4 balls in the same bin. That's a very small probability. Now apply the previous formula, which kind of says that the probability is slightly higher than that. So if you apply that formula now, 500 choose 4, 1 over 1000 to the power 4, and 1 minus 1 over 1000 to the power 496. If you do this, it works out to be about 1580 in a million, or 0.00158 is your probability, which is significantly higher than 10 to the minus 12 that we thought as a naive approach. So keep in mind that the hash collisions are very highly probable, and there is a very famous problem called the birthday problem that shows you that if you have a room full of people, and if you want to figure out what is the probability is 50, what is the number of people that you need so that the probability is 50% that two people have the same birthday, it turns out the answer is the number of people is 23. And that's a fairly small number of people. If you have 23 people in a room, there's a chance that there's 50% chance that two people have the same birthday. Right? So that's a surprising fact. And you can see it here that applying this correct mathematical formula, we can see that the probability is fairly small that in case you have 500 balls that you want to throw into 1,000 bins, what is the probability that 4 of them end up in the same bin? And that's our first, there's a first indication that this is a more difficult problem. It's going to be difficult to design this hash. Now let's firm this up by saying if we were a hash designer, and let's say this formula that we had looked pretty ominous, it looks pretty complicated, all this calculation here, it looks a little bit more complicated. So if we simplify this function actually turns out, if you do some simplifications, then this formula becomes something known as a Poisson distributed formula. Under some simplification, it looks kind of like this: lambda to the power k e to the power minus lambda over k factorial, where all the assumptions are the same, that this k is the number of items in our bin, and this lambda is nothing but m over n. M over n is our lambda, and that is m is the number of balls we're trying to throw into n bins, and k is really, how many items you can really store inside one bin, the capacity of each bin, right? So that is the formula. Now, if we apply this to this, let's say I'm a hash designer and I want to have 16 million entries that I want to store in my hash table, and the hash table has 32 million elements or bins, and then each bin can take up to 4. Beyond 4, it'll overflow. So the way I would implement this is that, let's say I have a linked list or number of columns that I can match inside the hash table, and the number of columns is 4. The total capacity of the table is that, we have 128 million entries and we are only storing 16 million entries. So the table is about 1/8 full, right? About 12% full. In a 12% full table, if you only have four elements inside each bin, then our probability is going to be, let's go back here. Our probability is 0.158%, or 1580 in a million. 1580 in a million is our probability. So it's still pretty high. It's a very high probability if we want to keep this m equals 16 million, n equals 32 million, and we only have 4 columns. Now, what if we double the number of columns and reduce the number of rows, number of bins? So we could do it this way. We still have 128 million total possibilities, and we still have 16 million balls. But if we reorganize the table so that it has more capacity inside each bin, rather than more number of bins, we have less bins now, but we have more capacity inside each bin. Now what's the probability that we'll fill up to 8? So now we're trying to figure out, if we fill up each row or each bin, we need 8 balls. So now to reach 8, the probability is 9 in a million. So it's significantly improved probability, because getting 8 collisions inside each bin is 9 in a million. Now, if you see, getting 4 collisions inside each bin was only 1580, was 1580 in a million, right? So probability was much, much higher. So the more columns, the more elements we have inside each bin to handle this. The size of the bin matters significantly. The deeper you make the bin, the probability goes down significantly. So that's the fun fact about the hash. So in a sense, when you design your hash tables, I would say if you go back to our original slide, when we design this hash function, sorry, when we design this hash table, we should make sure that we keep the number of columns or the chaining much bigger so that multiple elements can go inside each row. And so, like we saw, if we had 8 elements inside each row, getting up to 8 was very hard, but getting up to 4 was easier because the probability was much higher. So the best thing to design in your hash table is to have lots of columns or lots of chaining, lots of elements, a lot more capacity inside each bin or bucket in your hash table. That's the main idea. That's the core idea. And now you can see how all the pieces fit together, the math behind it, how it works out that this Poisson function tells you that the probability is much, much, much higher if you have less and less columns. So you're better off going the other way and having more columns and designing a hash function that works much, much better and flawlessly in many cases if you design it correctly. So that's it for today's video, guys. Hopefully you liked it. If you have comments, if you disagree with my explanation, the way this math works, if you want to improve upon it, leave me some comments and I'll catch you another video. Until that time, take care and goodbye.